Can you hear me? All right. First, there's an error in my title. It should be exploring PFAS and many other compounds and consumables goods using GC by GC and high-resolution time-of-flight mass spectrometry. Let me get this right. Just a short outline of my presentation. There'll be a background and objective, a little bit on the experimental because I want to spend some time on the results in the discussion. We'll look at something simple that we did a while ago and then repeated using some of our analytical methodology. That's looking at anti-fog solution, and also that's for making a case for our HRT instrument or for high-resolution time-of-flight mass spectrometry. And surprisingly, we'll look at chewing gum. Why? Well, it'll show us sort of how we can screen through that complex matrix. That was new to me. I didn't realize chewing gum was so complex. But I think that most of you have heard about PFAS components or xenobiotics that are used widely in industry. People are becoming more aware of them in current times, but I just have a few examples here. I have a acid, I have a sulfonic acid, a sulfonamide, and some afluorotelomere alcohol. And the compounds that I've been looking at include ski wax, they include some special lubricants that we're looking at, dental floss, chewing gum, and of course, as I mentioned, anti-fog. The instruments that we used were the LECO Pegasus BTX to start off with, and then the high-resolution TOF. As far as sample preparation, it's very easy. I try to stay away from manipulating the sample too much, so it's either dilute and shoot, as I did with liquid samples, or I did thermal desorption, followed by pyrolysis in separate steps. And let's start off with example A. And I personally use anti-fog quite a bit in the lab, but also for hockey and for skiing, and something that I still use today. In fact, I was using it last week. The problem is, and this was pointed out by Stapleton a while back, that some of these PFAS solutions, or some of these anti-fog solutions may contain PFAS compounds. If we could select one of these PFAS or these anti-fog agents, and we can run it and get the simple chromatogram. And this is one that we obtained with our BTX, and it's quite simple. But it actually turns out that there's quite a few components in there, and you'll find different classes of organic compounds such as alkenes, and so forth. You can read the list. I wasn't really interested in those because there are also quite a few unknowns. And in fact, those unknowns were the primary components of this anti-fog. That was not true for all the anti-fog samples that we bought from Amazon. But there was a few that had potentially PFAS components. Fortunately, the library at that time that I used, I think, was NIST 20. NIST 23 is a little bit better. It's starting to have more PFAS compounds in the library itself. But I was able to identify through automated processing, fine processing, a few of those, 1 through 5. But X, which I'm going to focus on, and then compounds 6 through 14 were unknown. They weren't in the NIST library at that time. I don't think they still are. They aren't in that library. They were not in Wiley library, and they were not in ChemSpider, and I checked multiple times. So if we focus in on ChemX, you process the data, and you get what we show there. Our data is on top. It's the peak true. We really don't know what we have. You're relying on automated processing. You get a spectral similarity score that's ridiculous. So what's the solution? Well, you're going to switch over to high resolution time of flight mass spec for unknown characterization. We do have resolution here, but it's spectral resolution that we're looking for. We also have the ability to conduct multiple modes of ionization, both electron ionization and also chemical ionization, both positive and negative. And of course, we can determine formulas with a high degree of confidence. So let's do that. We ran the same sample, and we're showing X, that compound of interest and unknown, now with the HRT. And you can see that there's 5 places after the decimal point, so indeed this is high resolution, accurate mass data. And there's our instrument. It's the HRT, and we, of course, there's a couple of different sources that you could use. We used a multi-mode source for all of this work. And after processing the data, it was still an unknown. Peak table that really didn't tell me what it was. But we also get a lot of additional information. Since we can calculate formulas for that fragment, and in fact, any of the fragments in that spectrum, we can determine elements of unsaturation, or RDBE, ring double bond equivalence. And it happens to be that that's a fragment. In addition to that, we can calculate formulas with a high degree of confidence because we're talking about not mass delta or error anymore. We're talking about mass accuracy, which is defined in the box. Observed minus calculated divided by calculated, again for any of these ions, times 10 to the 6th. And it turns out that we can use that then to calculate formulas for any of those fragments. And in addition to that, yes, there's more, right? We can use the same source. It's a multi-mode source to collect CI data. And that's where the power starts to come in. Because that EI data, I'm going to show you a lot of this skinny data. That's a term that I stole from Jack Cochran. A lot of the old school guys remember Jack Cochran used to use that terminology. There's not a lot of information in that EI spectrum, but there's a lot more in the CI spectrum. So if you look carefully, where I didn't have any molecular formula information, switching over to CI, in this case positive CI, I get a strong protonated molecular ion with an excellent mass accuracy of parts per million and a formula that's associated with that. And since the reagent gas is methane, there's even more, right? So you're gaining confidence because not only can you identify and get information about that protonated molecular ion, you can also get information about fragments and additional adducts. This is the M plus 29 and the M plus 41, which are common adducts when you use methane as a reagent gas. In addition to that, you can do this in LC. We can do it for GC data as well. This is the observed protonated molecular ion cluster. The software generates a theoretical molecular ion cluster and compares them and assigns a value. That's your isotopic fidelity score. And anything above 900, that's great. So you got a formula, and you're pretty confident about that formula, but you don't have the most important, right? And that's the structure. And that's what we try to get next. As I mentioned before, we failed as far as the NIST library, the Wiley library. Ken Spider doesn't have it. I got lucky. I had Stapleton's paper from Duke University, and I also had the EPA CompTox library. And I had some choices. Once I did an external database search, I got 4 choices. I chose that particular one because it seemed the best fit. There was also evidence in the EI spectrum that I was dealing with glycol type material, CH2, CH2O, and so forth. No identification, no annotation, but at least I have pieces of evidence that I'm putting together to try to determine what I have. Furthermore, once I have that information, I can determine perhaps potential structures for the other unknowns. Because I have an idea of what X now, What about 6 through 14, where they're actually related, which is kind of neat. And I can start speculating about structures like this oxonium ion for particular fragments for unknown 6 now. So I'm going along the line. And I can run sort of the same type of methodology. I can run the complementary CI data and now get a strong protonated molecular ion with a good mass accuracy, get a formula. There's extra information there. And I can get a tentative assignment based on all of that information. And I feel confident about that. In fact, I feel so confident that I took and assigned all the unknowns. I annotated them as polyfluorotelomer ethoxylates as shown in the table. So that demonstrates the power, of course, of high resolution time of flight mass spec. I didn't have to use GC by GC, not yet. So I go back to my second example, chewing gum. I love chewing gum, especially bubble gum. But I didn't realize how complex it is. You can look on the left now. That's an actual contour plot. It's actually a blob. That's what gum looks like when you actually take it up to 300 degrees Celsius and run it through your HRT instrument. There's a high degree of complexity, large sample constituents. There's a lot of degradation, especially with sugars. If you have sugar in your gum, of course, there's sugar-free gum, and we looked at both. But there's a lot of degradation, and the different components have different chemical and physical properties, and of course they're present in a wide concentration range, which can be a problem because the compounds that I'm looking at, for some reason, they're at very, very low levels. It's quite annoying. See, there's a lot of other stuff in here. And by the way, I put that slide up. That's actually, this is the same sample analyzed using the BTX. I also had false positives using the HRT. I said, well, yay, I have found the PFAS. Not really. I don't know if you would be confident in this number here. I don't know, 800? Most people would be pretty confident, but this is one of those skinny spectrum that I talked about earlier. I don't have any confidence with that, right? Despite this number. There's no molecular ion, and so this particular annotation is false. In fact, I confirmed that using the tools that I'm going to show you. So here's where the power really is. This is the ultimate. It's when you combine not only high resolution, but also GC by GC. And I don't have to tell people in this audience about that. But then there's more. It's also the software. And that's what I'm going to show you as well. So I acquired both a set of data for each of the samples that I ran. And I ran a variety of chewing gum samples, wrappers, and the containers, boxes, if they came in boxes. And we can discuss that maybe offline if you're interested in. But I'm going to focus on the gum today. And if I zoom in, there's a lot of complexity to the sample. You can see that there's different components. You can see on top there are sweeteners. There's the gum base. It's kind of funny because that's what I was really after when I started looking at gum, is what is the base of gum? You can chew it for a while, where there's some polymeric material in the chewing gum. And I was looking to identify what that was. And of course, there's other ingredients for softness, for flavor, and etc. To get to the polymeric material, I had to go from 300, in this case, to 700 before I started seeing some of the degradation products of that polymer base, which is polyisobutylene. You start seeing butene, but also dimers, trimers, tetramers. I think I'm only showing trimers and tetramers in this case up on the screen, giving you some examples. So in this chromatogram, there is some beauty. You can start seeing some of the patterns in that chromatoblob. But here they are, right? The sweeteners responsible for that sweetness and flavor. And I can't analyze the sugars directly, and I am not derivatizing here. If I'm derivatizing, I have a good chance of seeing some of those sugars easily. But I can see the evidence. There's a lot of furans in that blob that I showed you earlier. There's a lot of dehydrated sugars. And some of those are listed here. I also have flavoring components. This particular gum, this wasn't the citrus one, this one's a spearmint one, handed to me by our product manager. Yeah, that's this sample, that spearmint gum. So it's not surprising that you have monoterpenes, you have sesquiterpenes, you have diterpenes, and all those good things that you find in essential oils. And you also have preservatives, as I showed down below. The gum has to be soft, hopefully, right? After you chew it for a while, you don't like hard gum. Maybe some people like hard gum. Glycerol tends to be a softener as well as glyceride. So I'm showing a mono acylglyceride as well as a couple of triacylglycerides and associated fatty acids. But I haven't answered the question, well, I sort of did earlier, right? Are there polyfluorinated alkyl substances in the chewing gum that I analyzed? Maybe specifically this sample. And the answer, fortunately, is no. Not in the chewing gum, not in the wrapper, not in the box that it came in. That's good news. So how did I do that? Because it's kind of tedious, right? I'm going through peak tables. I don't like doing that. I don't have that kind of time. Even though I have powerful filtering tools, I have the power of high resolution accurate mass. I know where these compounds tend to split, and I know how to target these, but that's too much of a pain. So what I wanted to show you is how we screen for this easily. There's 3 steps there. And basically, the first 3 steps are to find the needle in the haystack or the PFAS in the blob. And that's where the spectral analysis tools comes in. The last step, you still have to do some characterization. Often when you're at traced levels, automated peak find doesn't work. So you may have to go old school. And fortunately, with high resolution accurate mass and chromatoph, we have those tools. Sometimes you get lucky, and I'm going to get lucky here because I spiked these PFAS compounds in the sample. But I sum all the ions in the contour plot. That's a complex plot. I develop a mass defect plot. On the y-axis, it's just mass defect. On the x-axis, I actually am plotting high resolution accurate mass. And the definition is there. Then I can target not 1, not 2, but a whole series of PFAS components. I don't have to look at them individually. I can target the tail because I know how these fragments, and I know that each CF2 is 50 m/z apart. And so I can build a target list or a mass defect series as shown on the left. I have a FC prime that's for odd, but I can also target even. Those are for the tails, and I also can target the head. In this case, I have that last entry there. It's to target the head, for example, of that acrylate species. And then I can use spectral analysis tools to take that complex mass defect plot and just show the compounds of interest, or the ions of interest, excuse me. They are now in the horizontal plane parallel to the x-axis. And each of these are 50 Daltons apart here. And these are the PFAS fragments. And in addition, I've scaled it according to this scaled mass defect plot has been scaled according to the equation in this rectangle. And as I mentioned before, I can also target the head in this species. And there they are, the PFAS samples. So those first three steps occur, again, just to locate those trace components in the sample. You still have to characterize it, right? And that's where the mass spec data comes in. More specifically, the high-resolution mass spec data. And you can have a molecular ion. It's still skinny spectra. I trust this one, and it looks like I didn't get my spectral similarity value, but if you squint very high, you can see that it's above 800. But more importantly, I also have mass accuracy for that molecular ion. Just happen to have one in that case. In some cases, you don't have, oh, there it is, popped up. On the right case, you don't have a molecular ion. Again, skinny spectrum, that's not a problem because I always acquire. My standard mode of operation is EI, and then I automatically acquire CI, both positive and negative, because I'm usually in what I call discovery mode. So I don't have the molecular ion, no problem. I can get the protonated molecular ion, I can use the isotopic fidelity and gain confidence in the annotation for this compound. And if the standard is readily available, I can purchase it and run it and then be really confident that that's the compound. So I recommend, as GCxGC-HRTOFMS as a general screening tool. It's a lot more than that, right? Because it gives you so much information. But as you see, you can easily screen for example, for PFAS, but also other classes of trace components, such as polychlorinated biphenyls, other POPs or persistent organic pollutants. It's easy to do. And you could use a combination of EI and CI, of course, to gain confidence. You get those formulas, and then you can gain confidence in the annotation. And then if you're really looking for fast screening, you're not relying on processing necessarily, right? You don't have to do peak fine processing to do this. You can use mass defect plots to target those needles in a haystack. And with that, I'd like to thank you for your attention. And if there's time, I'd be happy to answer questions.